Today we're going to take a look at 4.2, logarithmic functions and their applications. So in 4.1, I know it's been a couple of class periods now, what we looked at is we looked at exponential functions and applications. And there is a reason that these two are put back to back. We'll get there shortly. But first, we're just going to talk about log functions, their applications, and then we will make connections after a bit. So logarithmic function is a function f of x equals log base a of x, where a is bigger than 0 and a is not 1. Now, be careful. Most of you have calculators that do not have a log with a changeable base at the bottom. If you have a calculator like a TI-84, TI-83 calculator, and you see one that says log, it is not log with your ability to just change that little number down there by it right here. Okay? It's automatically going to put in a log base 10. You're not going to see it, but if you just type log, it's going to understood be base 10. So we'll talk about how we change all that when we're working with the calculator perspective of that later. But to start with here then, my domain and my range for logarithmic functions, my domain is actually 0 to infinity, and my range is negative infinity to infinity. And I'll just sketch you, we're not doing graphs specifically right now, but just to give you some sort of sense of what's going on here, let me sketch you a graph of what a log function basically looks like so that this will make some sense. Roughly speaking, looks like this. So you can see that the domain is in fact 0 to infinity because it's just the right-hand side of the graph, and that the range is everything. Goes up, goes down forever. There is the one that I mentioned before, something called a common log. A common log doesn't say anything down here, right? It's actually understood to be a base of 10. So this log here is really the same as log base 10 of x, okay? It's called a common log. Base 10 is a very common base. What's the base 10 is it's the base we use, right? So this is why it's called a common log. It's the one that if you just hit log in your calculator, it's the one that will show up. And then the other log is the natural log. And this actually looks like ln. So in English, we do this thing that some other languages don't. We put our adjectives before our nouns. I know this is not English class, but we say things like big house. There are other languages that say it reversed, right? They identify the noun first and then they put the adjective behind it, so they would say house big. Right, so like one of my favorite restaurants when I was a very little child, and I don't think it even exists anywhere anymore, was a place called Casa Bonita, Mexican restaurant. Okay, do you guys know what casa means? House. What's bonita? Pretty. So it would say Casa Bonita, it would say house pretty, right? Pretty house, right? So it's got this weirdness to it, right? Casa is house, and so it would say house pretty because that's what Spanish does. They put their adjectives after their nouns. Now, why am I mentioning that? Well, that's actually what's happening here with ln. This is log natural, right? It's the natural log. So that's what you're seeing happen here because this is not based in our language of English, okay? So we're looking at the base of e. So this is understood to be log base e of x. That's what it actually is. Natural log is log base e of x. Yikes. Okay, so you've got two buttons in your calculator for logs. One is the common log and one is the natural log. You do not have one for other general logs, all right? There's some ways to change it, and we will do that. We'll get there, I promise. But I'd like to do a couple other things first, and this actually relates our idea of exponentials from 4.1 to our idea of logs in 4.2 and shows the connection between the two. So here are a couple of examples. This is log base 3 of 81 equals 4. And then I have log of 1,000. So this is log base 10 of 1,000 equals z. And what we're going to do on this one is not solve anything. We're just changing forms. We're changing between a log form and an exponential form. And if you're in Oklahoma, at some point you're bound to see one of these. I promise you. Has anybody seen, like legit, in the wild, in your home, a scorpion before? Yeah, me too. My husband really needs to spray the house. Yep, like recently. Scorpions and spiders. We live a little bit out in the country, but yeah, scorpions and spiders. So what I'd like for you to do is to circle the 3, and you're going to draw an arrow around, and it looks like a scorpion tail. If you hadn't had an opportunity to see a scorpion, just step on them when you do, if they're in your house. Do not mess with them. By the way, cats are impervious. Cats are impervious to their sting or their venom in their sting or something. So my cats think they're really fun to play with. My kids have both been stung. The 2 that were at my house at the time when they got stung, Abby and Eli, have both been stung by a scorpion in our home before. It's not fun. It holds, like the sting holds for quite a while. All right, so this looks like a scorpion tail. So this is the image that you want to have. You always circle the base first, right? The little subscript part, and then you draw the arrow to the other side and around. All right, it's got to go to the other side first. So what are we going to do with this now? Well, we're going to follow our arrow. That 3 will now be the base of an exponential. If you follow the arrow around, it crosses to the 4 next. That will be our exponent. And then it equals where I land, in this case, 81. So I'm not solving anything right now. I'm just rewriting on these 2 problems. So do be careful to pay attention to what your problem asks you to do. This just says to write it as an equivalent exponential equation. Does not say to solve. We have this tendency to always want to say x equals at the end. Be careful. That's not what this question asks for. Okay, so this is the correct, appropriate, adjusted form in exponential, right? So we can do the same thing on part B. What number will we circle?
10.
The 10. And we will draw our arrow all the way across the equal sign around to land right next to where the 10 was to begin with at the 1,000. And as we rewrite, it will be 10 to the z equals 1,000. And make sure that this value on the other side, this case the z, this case the 4, are written as an exponent. It's not multiplication, it's a power. Okay? Everybody good so far? Lovely. All right, now we're going to go the other direction. We're going to start with an exponential, and we're going to write it as a log. You can draw the scorpion tail thing if you'd like again. It's a little trickier because of the way that it's set up, so I don't usually think about it that way. I usually reason through it with the exponents and so forth the way that they are. So the base of an exponent is the same number that will be the base of your log. So this is log base 10, because the base of the exponent is 10, so the 10 is written next. You're always separating these 2 pieces that are beside each other. We did it over here too. I didn't sort of make emphasis of it, but right, the 3 and the 81 get put on either side of the equals sign. Same thing happens here. The 10 and the 5 will be put on either side of the equals sign. So the 5 has to go on this side. And then this idea of log base 10 has no meaning unless there's a value next to it. The value next to it needs to be the w. It would be like you telling me square root equals 5, and I would be like, square root, that's not a value, that's an operation, right? Or you saying multiplication equals 7. No, this is a multiplication x, not a x, right? That doesn't make sense. So you have to actually have log of a value for it to make any sense. This is log base 10 equals w. Now, another possibility for how this could be written, if you were doing it in your calculator, if you were looking at the back of a book, if you were comparing it inside of my math lab, is they might just write log of w equals 5. Because log, as a standalone, without anything written down next to it, is log base 10. Okay? So this is one of those like or things. Either of these would be correct, technically speaking, but if you're looking at something like you're not being able to figure it out and you want to put one of those buttons that says show me an example and they do that, I want you to know what that's doing. It's really log base 10. Okay, on part B, same thing. This is log. What's the base of this exponential? It's b, so that will be the base of my log as well. We're separating things, so the k goes on to the other side, and the z is next to it. Every now and then I have students have difficulty sort of writing what this looks like in an appropriate way. So let me verbalize what this should look like that you're seeing. This should look like a subscript, right? The b here. the 10 here, those should look like subscripts, just like you're doing an English paper or something like that. It's a subscript. The log and the z and the k, they're all on the same baseline. The log and the w and the 5, they're all on the same baseline. So it shouldn't look like you've got a 10 with a power of w. The 10 is the base. It's usually written significantly smaller, even just notationally speaking, because subscripts are do that. But the w, the 5, the log are all written the same size and on the same sort of horizontal line. Okay? All right. So this is just the ability to rewrite on those two problems, going back and forth between those forms. What we're going to do in number 3 is we're actually going to solve something. Not really solve, but simplify. It says to find the indicated value. Now what you'll notice is there doesn't happen to be an equals sign anywhere on these, right? Awesome. Don't tell me because I'm going to share later, okay? All right. So there aren't any equals here. So what we're going to first do on the first problem is we're going to write equals whatever your favorite letter is. X is as good as any. Okay? So I'm going to write equals x. And our goal as we do these is to use that exponential form that's more comfortable. Let's be real. Like you're more comfortable in exponential form. Maybe it's not your favorite, but it's better than this log thing. We're going to rewrite this in exponential form in order to be able to make a claim on how we solve it. Okay, so we wrote equals x, and we're going to use that scorpion tail to rewrite. So I'm going to circle my 2 and draw my arrow around. And I'm going to rewrite this as 2 to the x equals 16. Okay, is everybody okay with that? Now, you might be able right here to just say, well, I know what x has to be. That's great. If you don't, what you're going to do instead is you're going to try to get them to have the same base on both sides. Well, one of them's already got a 2, and a 2 can't factor any smaller. But 16 can. If you were to take 16 and you were to factor it, 16 is what? 8 and 2. And 8 is? 4 and 2. It's okay. And then 4 is 2 and 2. There's 4 2's, right? 1, 2, 3, 4. So if I were to rewrite this, I could write this as 2 to the x equals 2 to the 4th. And we're kind of back where we were in section 4.1. And then what I would know is that my x equals 4. If the bases match, the exponents have to match. Now, if you know from here that x has to equal 4, that's fine too. This one's a pretty straightforward one. It's fairly small. 16 is not a huge number, but the bigger the number is on the other side, the less likely it is that you're going to be able to do it that way, right? If you had 128 on the right-hand side, you might be a little bit more stuck than if you had 16. So feel free to factor things if you're stuck, but if you know it, you can just use the fact that you know that 2 to the 4th is 16, so x would have to be 4. All right, let's try part B. This is a little too large for my liking at the moment. Okay, same thing. We're going to write equals a variable, your favorite letter, whatever that would be. I had a student one time who always used the letters that were the initials of her friends. She liked to use L's, which is terrible to use, by the way. Don't use an L. All right, so we're going to circle the base and draw the arrow around. So my base is 1/5. Power is x, and it equals 25. This one is not near as clean as the last one. 1/5 is not a very pleasant looking base. It just isn't. But it could be rewritten to have a base of 5, much nicer. So how could I rewrite 1/5 so that it's 5 to a number? No. Make it a -1 as an exponent. Now, I still have this x that's dealing with this here, like that. So all I've done is I've replaced the 1/5 with 5 to the -1, because I'd like to have a whole number to a power. Much easier to work with than fractions, okay? So I've got the whole number 5 to the power -1. Well, is there a way to write the 25 with a base of 5 as well?
5 squared.
It is 5 squared.
So it's going to be -2?
Yes, let me take one more step to get there, but you're correct. So one of our properties of exponents says that when I have a power raised to a power like this, right, 5 to the negative 1 times x, right, the negative 1x, that we multiply those. So this is 5 to the negative x. I'm a little off my screen. I told you my screen's not near as big when I do this. I'll just shift it up a little bit. Okay. Is everybody okay with that step? Yeah. And then just like you mentioned, Maxwell, those exponents would have to be equal then. So I have negative x equals 2. And if I divide by negative 1, then x is negative 2. You're going to have to show me some work if you're doing it on a quiz or a test. Okay, that'll be good. All right, so I'm going to show you how you can check the ones that are like this on A and B where they have those different bases. I'm going to show you how to check those a little bit later, and you can verify that you did it correctly with your calculator. On C and D, you can actually get those directly from your calculator. So I'll confirm that with you here in a moment, but we're going to do it out by hand to show what's happening as well. All right, and that's what I would expect to see on your paper. So to start with, we're going to write equals x. Perfect, Kaylee. Thank you. That was my next question. It is a base of 10 because it's a common log. And then we'll do our scorpion tail. So now I have 10 to the x equals 10. I think you guys can probably tell me what's x. X is 1. Now, if you grab your calculator and you just type log 10, it will tell you 1. Okay, did that work? Yes. Anybody who did check it? Okay. Now, the next one, same thing. This has got equals x. This is a log base e, right? That's what natural log is. It's log base e. So we'll circle and draw our arrow around. So it's e to the x equals 1. When I have any base to the power x equals 1, what power makes that happen? 0. Okay, any non-zero value to the power 0 is equal to 1. And also, we know that our base is always going to be non-zero. That was how we defined our log functions over here. Did you notice that? The base is always positive, so it can't be 0. Okay, cool. So e to the 0 is 1, means that x is equal to 0. And again, if you grab your calculator and you type in ln, there's a button that says ln, 1, and hit enter, it should say 0. Okay, to do that? Fabulous. Okay, let's talk a little bit about graphing now. I mentioned very briefly graphing over here and drew sort of a sketch for you. I'd like for us to graph a couple of things simultaneously. In particular, I'd like to graph the equation for y equals a to the x. And you did that back in the last section that my math lab was uncooperative with you for. But you should have had the basic idea, that's not very good, that this was the graph of y equal a to the x, right? Agreed? Okay. And what I drew for you a moment ago is that my log graph looks something like this. And this is y equals log base a of x. Now imagine if you put a line right here and you fold it along that line. What would happen?
Wait, can you say that again? I wasn't looking.
The dotted line, if you took that dotted line and you folded the graph up along that dotted line, what would happen? It wouldn't make a parabola. Somebody else said something about
It would flip.
they would be the same. The graphs would line up right on top of each other. So if you took one, or you can think of it, if you take one side and you fold it down on top of the other side or up on top of the other side, the graphs would actually line up perfectly, especially if we'd drawn them perfectly. They would line up perfectly. Now this dotted line is very specific. This dotted line, is the equation y equal x. It's our standard line equation, y equal x. Now, we're talking about this graph right here, all right? So I just want to talk about that new graph, that log graph, as I write down some features about this graph. The vertical asymptote here. What is acting as a vertical asymptote on that graph?
1.
Say it, Divine. Not the dashed line. I only want to think about, in fact, I'll delete it for the moment. I'll put them back. Oh, that's not what I meant to do.
Are you asking for the...
Just this line. All I want is that curve.
Okay.
What's the asymptote?
1, maybe?
Nope.
0.
Okay, what's 0? X equals 0. The y-axis, right? The y-axis is a vertical asymptote. And it is an asymptote, right? Because down here you can see it's getting really close. Agreed? So we do have a vertical asymptote for my log graph of the, I'll write it here as the x-axis just as a reference point, but the equation of it is y equals 0. I said that wrong. I said all of it wrong, didn't I? Got them backwards completely. This should say y-axis, and then it should say x equals 0. So sorry. We fixed it really fast, though. It's almost like it didn't happen. All right. Any guess as to what this x-intercept here might be?
1.
It is at 1, actually. Yeah, you're right. So it's actually at 1, 0. And it kind of makes sense because if you'll remember, the intercept over here for my y-axis was at 0, 1, right? That was for my exponential graph. It was at 0, 1. So for my log graph, it will be at 1, 0. Okay, so this is what happens when we have the equation where we have an a value that's bigger than 1. Now, when we have an a value that is between 0 and 1, the graph looks like this instead.
Oh, so it's just kind of like the opposite direction.
It flipped over the x-axis, right? That's what we did when we had that happen. Now, if I put that dotted line in again, and I reflect over it, I'll do it in yellow so that I have a reference point in terms of saying the language of what I'm doing. Oops. Roughly speaking anyway, it looks like that.
What did you do again?
All I did was that I reflected it over the dotted line. Okay? So another thing you could think that I did is that I simply drew the two graphs on the same axes and I compared them with the dotted line. That's how I did it last time. The white graph was the exponential graph. It's just that it's an a value that's between 0 and 1. The yellow one is actually my log graph. It's just that my a value, okay, I don't have space there to do that. Let me shift it a little bit. My a value is between 0 and 1. So that's why it's going downhill instead of going uphill. The interesting thing is that the vertical asymptote and the x-intercepts don't change. So my vertical asymptote here is still the x-axis, I said it wrong again, the y-axis, which is x equals 0. And the x-intercept is still 1, 0. I want to draw one more graph overlaid on top of each other to show a relationship, but I'm out of graphing space, so I'm going to delete one of mine. So if you want to draw my last graph, you can, okay? The graph I want to draw relates the two logs graphs to one another. So here's the first log graph that we drew, and here's the second log graph that we're going to draw. Okay, these are both y equals log
Oh, it's kind of like a lopsided x.
base a of x. This one simply has that the a is between 0 and 1, and this one has that my a value is greater than 1. If you were to compare these, they're reflections of one another as well. how are they reflected to get the other graph? How would I take the first graph? I'm not going to be able to delete it completely because my arrows are on the end. That one, the one that's still there. How would I take it and get that graph? What would I reflect over? The x-axis. It's an x-axis reflection. Back in section 4.1, we did the same thing with my exponential graph, and we reflected it over the y-axis. Do you remember that? And it just flipped it over the y-axis. This one flips it over the x-axis when I'm taking a value between 0 and 1 instead of a value bigger than 1. All right, so I am not at all sure what will happen on my math lab when you graph these. My inclination is that if there was weirdness going on in section 4.1, it may persist into section 1.2 or into section 4.2. I don't know. Let me talk about, from a standpoint of graphing it by hand, what happens, though, as we move forward. So this was, how did I get that? All right, that's what I want, number 4. This one actually has y equals, or g of x equals log base 8 of x. Okay, the important thing, the most important thing to start with is to recognize that this 8 is bigger than 1. Agreed? So in comparison to my first graphs over here, it's this first graph that I drew right here. It's going to have that shape. It's going to be an increasing graph from left to right. So as I sketch this graph, it's going to be increasing from left to right, like so. The x-intercept will still be, no matter what that base number is, it will still be 1, 0. Okay? So let's look at the 3 pieces that it asks us to identify here. It asks us to identify the vertical asymptote, the domain, and the range. What is the vertical asymptote for this graph? Yeah, it's still x equals 0. And it will always be x equals 0 unless I have something that's going to shift it. We'll see that happen in a minute. How about the domain? Yep, it's 0 to infinity, right? It's just the right-hand side of the graph. And my range? Negative infinity to positive infinity. That's my range. Okay? So the base being 8 as opposed to 2 or 100 or 50 or 67.329, they're all going to look the same, at least in terms of these attributes. What would they actually look different? Like, what would be the difference? Obviously, there's got to be something different, or it would matter what the number is down there, right? And what it actually looks different is it actually would look different on how tight this graph is, if you will, to the x and the y axes. If the graph has a bigger base, then it gets narrower like this and like this. So it hugs closer to both of the axes. That's what happens as the x, or the base value, gets bigger. If the base value was narrower, but still before you get to, a number smaller than 1, it becomes wider looking and it becomes shallower down here. So there's not something that we do to draw that differently, just so you know. I'm just letting you know that that's what's happening with those numbers, okay? So they do have effect. The effect's just not very drastic. Okay, this one actually has a lot more going on, way a lot more going on. So let's identify, based on transformations of functions that we did back in chapter 2, what all is going on. What about, let's just start inside with the x. We have a -2 here. What is that going to do to my graph? It is going to shift it right 2. Okay? Now, the easiest thing to do when we're shifting right 2 is to recognize that that vertical asymptote's going to move. Correct? It's going to move right 2. So over here, I'm going to start by shifting my vertical asymptote right 2. So this vertical asymptote now is the equation x equal 2. Is that all right? Cool. What is this plus 3 at the end going to do? Yep, this one's going to move it up 3. Right? There's one more piece that I need to address. What is it? Yeah, the negative at the beginning. What is that negative in the beginning going to do? So is it going to flip it over the y-axis, or over the x-axis? It's going to flip it over the x-axis. Okay, so this is a vertical flip. Because it's happening on the outside, so it's happening vertically, which means it flips over the x-axis. You could write it as that it flips upside down if that helps you. This is just for your benefit, whatever language it is that benefits you. It's not formal like language. It's just your benefiting of your language. Okay, so we shifted it to the right. We did that. We would want to shift it up 3, right? And we'd want to reflect it down. So we could do the reflection down first and then the shift if you wish, but the shift will actually end up being down 3 then. So let's be a little bit careful. We want to do a reflection down first, so we want to be careful. We're moving from the inside out. Let me say it that way. We started with our shift of the -2, right? Moved it right 2. The next thing that's attached is multiplication of the -1 in front. We're going to flip it down next. So we flip it down 3. I'm sorry, not down 3. We flip it down. So what it was looking like was this. If we reflect it down, it actually looks like the other graph, interestingly enough. And this point right here is the point, what? I haven't done my shift of 3 yet, but what is that point? It's 3, 0, yes. And then I need to move it up 3. That's my last piece of information. So we're going to move this up 3. So this is going to be our new point right here. I'll draw it in yellow as my final graph. And I'm going to identify that point. This point is now the point 3 because it was already the x value of 3. And I shifted it up 3, so it's going to be at 3, 3. Okay, so just like with transformations before, we're working from the inside out. So yes, I need to shift it up 3, and yes, I need to do a reflection, but I need to make sure I'm doing them in the correct order. The reflection comes first because it's multiplied by what's going on. The addition or the shifting up by 3 happens second because it's added, and addition happens last. Order of operations. So we end up with a graph that looks like this. Now, does the graph cross the x-axis? It does. But that's not a point of concern. That's not what we're going to be graphing. It's going to cross really far out, by the way, too, most likely, especially if we shifted it up 3. That's a lot of a shift up. So be careful as you're moving it. The point that's of concern as you're plotting it, and maybe this is what happened in my math lab for 4-1, I don't know. The point that's of concern is the point that's shifted, not the point where it hits the axes. Okay? Are we good with that one? Okay, we have one more component in this section. And that component feels a lot like what we did over here. Okay, it feels like this finding indicated values section. The difference is that it actually sets up an equation to start with that we're solving. We created an equals x in each of those previous problems, so we created the equations to do that. This one's just already set up in that equation form. So there's several different types of equations that come into play when this happens. Some of them are very nice, and they become ones like this, where I have 2, I raise to a power, and I can do some funny things by adjusting bases so that they match, and I can solve. Sometimes they're not quite that nice, so we're going to see both things happen. Now, to start with on problem A, we see something that's in logarithmic form that we can change into exponential form with our scorpion tail. So I'm going to circle my 4 and draw my value around like so. And I'm just going to rewrite it. So this is 4 to the power 1/3 equals x. Okay. We did that on our earliest problems, just the rewriting step. And I said, make sure you notice. It just doesn't tell you to solve it so you can stop. Well, this one does want you to solve it. Because everybody okay with the rewrite first? Excellent. Now the cool thing is that this is actually already solved for x. It says x equals something, doesn't it? Now the bad thing is that 4 to the power 1/3 is a very awkward way to leave your answer written. There's a cleaner, nicer, better way to write it that we have encountered before back in intermediate algebra and you didn't like it. Do you remember how else you can write? It's with radicals. And we're not going to simplify anything. Hold tight, Maxwell. We're not going to simplify anything. We're just rewriting it knowing the way radicals are rewritten. So this actually is the same as the cube root of 4. And there's no simplifying that can be done. But let me remind you, a to the m over n, I'm still on my screen, good, is equivalent to the nth root of a to the m. That's the property that we are using here. 4 to the power 1/3 is the cube root of 4.
Okay, that wasn't that bad.
Okay, it's not that bad, I promise. I'm trying to remember where it is. I'd show you. Okay, it's the next lesson where I show you how to confirm some of these things with your calculator. So, all right, part B. The problem on part B is that the value I'm solving for is in the exponent. Do you see that as a problem? Mm-hmm. Yeah, me too. And so as much as I don't maybe want to turn things into logs, that's the only way to get that exponent down. Because I cannot change the number 12 to be 5 to a power. I mean, it just isn't, right? It's not a 25. I don't have the value on the right-hand side, something nice that's 5 squared or 5 cubed or 5 to the 4th. I don't have that here. And since I don't have that here, logs are my only way of getting that exponent down. So we're going to rewrite this in log form. This is log base 5. If you remember, we're separating these two pieces, so the 3 minus x comes over here, and the 12 comes here. That's what we did when we separated them before, when we rewrote them before we separated them. Now, the goal is to solve for x, right? Get x alone. So what would we do next? We can subtract a 3. Now, the interesting thing here is, maybe not interesting, but it's nice, really, is what it is. You can't combine that 3 with the 12 or anything else. You can't. Because that 12 is inside of a log. It's almost like it's, like imagine if it were under a radical. I can't combine something under a radical with something outside of a radical. I can't combine something that's inside of a log with something that's outside of a log. So I can't combine the 3 with the 12. It's just log base 5 of 12 minus 3. And then my last step would be to multiply or divide, however you want to think about it, by a negative 1. So this is actually going to be negative log base 5 of 12 plus 3 equals x. Or you could rewrite it like this if that looks kind of funky to you. You could rewrite it as 3 minus log base 5 of 12 equals x. Now, let me show you how you could actually confirm this one with your calculator, at least in terms of a, no, that's not really a good place to do that yet either. It's just in the next lesson. We're going to just pause right there and hold tight on that. All right, so this is what we have for our final answer on that one. 3 minus log base 5 of 12. That's as simple as it gets. Okay? Got 2 more, and we'll be done for today. All right. The exponent now is in the base of a log. Well, I got to get it out of the base of the log using exponential form. So that's why we're moving in and out of logs. It's because we want to be able to write down x equals. You can't do that if it's inside of a base or inside of an exponent location. So this is inside of a base, which means it needs to be rewritten. So we'll rewrite it like this. So we have an x. What's next? Yep, to the 4/3. That's an exponent. Equals 1/16. Fantastic. Now, that 4/3 is much like this 1/3 over here, right? The third part, the part that was the fractional denominator here, this 3, became a cube root. Yeah? Now, it just had a 1 right here, so I didn't write it, but this is 4 to the 1. There's still a 4 to the 1 here as well. So as I'm rewriting this one, I have x to the 4th, that it's still here, but now I have the cube root of x over here. Everybody good? Okay. This actually, as ugly as it looks, is going to have the most concrete answer of all the ones we've seen so far. You're going to like it, actually. It's better than the ones we've done. So we need to solve for x, which means we need to remove the cube root, and we need to remove the power of 4. And it actually doesn't matter which order we do that in. So do you want to deal with the cube root, eliminating it, or the power of 4 to eliminate it? Cube root, you guys chose the hard one. We'll do it. I know. I'll show you. Okay, here's why it's hard. It's because 16 to the power 3 is probably not something you've memorized.
Isn't it something?
Isn't it? What is it, Divine? You got a calculator going on back there. 4,096. Okay. So now we've got x to the fourth equals 1 over 4,096, right? It's just a really big number. That's why this is not the preferred way to do it. I'll show you how the other one works out just so you can see later. What would I do then to eliminate the power of 4? Fourth root. So I'd need the fourth root. I know it's the top two, but the fourth root of 1's 1, so it's not very exciting. I'd need the fourth root of 4096. So if you want in your calculator, you can do 4096 raised to the power 1/4. That'll be okay. Maybe you have a fourth root button. Some of you do. Maybe you know how to use it. What is the fourth root of 4,096? It's not, you're dividing by 4. We don't want to divide by 4. We want it to raise to the power 1/4. It's 8. It is 8. Okay, you want to see how to do it with smaller numbers?
Yeah.
Okay.
I have a question.
Yes.
How come I'm not getting 4,096?
Type, because you probably typed in 1 over 16. Type in just 16 to the power 4.
Okay.
That's probably what you're doing. Yeah. Which isn't wrong. You're just doing it. We just did it in a different steps. Okay. Let's do this. Let's do the fourth root part first. So, what is the fourth root of 16?
2.
It's 2. Okay, so this is still the cube root of x because the fourth root and the fourth power cancel here. This is a 1 on top and it is a 2 on bottom. The fourth root of 16, right? If I were to take 16 and break it down, I'd get 4 and 4 and I'd break it down and again and I'd get 2, 2, 2, and 2. The fourth root of 2 to the fourth is 2. And then if I cube it, I have 1 on top and 8 on bottom. The numbers just stay so much smaller. It's very friendly. Okay, last problem looks really scary. It's the easiest one we've done. Are you ready for this?
Hold on. Gotta write it down.
Okay. On D, do you notice that both sides say log base 3? Okay? They don't cancel, but it feels like that, okay? So it's kind of like the problems where we got them to say 2 to the x and 2 to the fourth or whatever. We said, okay, well, if the base is equal, then the exponents have to equal. It's the same thing. If you've got the log of the same piece on both sides of quantities, then what must be true is that their interiors must match. Have to. So while they don't cancel, they do become sort of irrelevant. Almost. And I'll show you the almost here in just a second. Now, this actually requires us to move everything on the same side, factor and all that jazz. So I'm going to shift my x squared over here to the left. And I'm going to go ahead and shift the 24 at the same time to the left. So that gives me x squared plus 2x minus 24 equals 0. We've spent a lot of time with quadratics. We would factor this. Sorry, I'm trying to hurry to get you guys out, so just bear with me. X and x, 24. I need a positive and a negative since it's a negative 24. Positive 6 and negative 4. And if I set each one equal to 0, yep, x is negative 6 and x is positive 4. Now here's the caveat and the thing you have to be careful about. This problem did not start out as a quadratic equation, agreed? Yeah. It did not. It started out with pieces inside of logs. And there was something very back at the beginning where we said inside of a log has domain values, right, x values that have to be positive. So whatever answers down here, I have to get positive numbers when I put them in. So let's see what happens when I try negative 6. If I put in negative 6 right here, 2 times negative 6 is negative 12, which means that this is not in the domain. It's extraneous. It's like getting a 0 in the denominator of a fraction. It worked because we did some manipulation that made it work, but it's not really a solution. We'll check 4 the same way. Obviously 4 works here. 2 times 4 is 8. But we need to check it over here as well. What is 4 squared? 16, and is 24 minus 16 still positive? Yes, so we do end up with a solution. It is possible at the end of this to end up with no solution still, okay? So you do have to check both pieces to make sure that either one or the other or neither might or might not work. Like, you check all of that possibility. All right, we're done.